Let me try.
Unmute.
Yep.
Hello? Can you hear me?
Yep.
Yep. Okay, good. Sorry about that. So it goes back to Shiki Koromoto, who won a big prize, the Yoga Moza Prize last year for his work on the theory of synchronisation back in the 1970s. And that's back in this window. Yes, there we go. Oh, yes, and that's working nicely. But I want to tell you something that is almost like the poster child of synchronisation theory, and it's used as the example. You know, Matt Parker and Hannah Fry, etc., and all the textbooks say, you know, that there's one example, which is the Millennium Bridge on the day it opened, and I want to bust that myth. So I'll tell you about the story of the London Millennium Bridge, and then I'll tell you about another bridge, which is kind of dear to my heart, having worked at the University of Bristol for 30 years. And I'll try and tell you a much simpler theory of why bridges go unstable when people walk across them. And it's the simplest theory ever. The theory is try not to fall over. That's basically what people are trying to do. At least that's what I claim. And then we'll go into a little bit of maths, but not much. It's evening time and we started late. And I'll tell you a few other things that I have been doing along these lines. Why synchronisation is important in power grids, why it's also important in hearing organs. I've also had a PhD student who just offended at the beginning of this week successfully, working on synchronisations of neurons in the pituitary gland. And then maybe some philosophical remarks about applied maths and the wisdom of the crowd and all that kind of stuff. And finally, a dedication, which hopefully will become apparent. Now, I don't think I can see anything that is showing me the time. Yes, I have my phone here. I know there's only one thing worse than the speaker starting late, and that is a speaker finishing late. I've been there in conferences where people have stood up and they said, oh, but I must tell you this is the most beautiful theory, and the audience are all completely switched off. They were lost on slide 3. I can remember one such speaker, which will remain nameless, and he came as a talk when I was a postdoc at Bath. And my postdoc supervisor, John Toland, I was sat next to him. John was a lovely man, very humble man. And this speaker was going, oh, I'm so sorry, this is complicated. And we had slides up with symbols in 6 different fonts, and each font meant a different coordinate system. And he tried to then give an existence proof, and he had to do some iterations. And he said, I'm really sorry, it's so complicated, but it took me ages, and I really didn't think I could do it. And I'm really proud I have. And there's more notation. And John said, or maybe I will attempt it, Irish accent, particularly as this is being recorded. I have a bit of history, unfortunately, of throwing recordings out by, God, I nearly said fuck, you see. And then people sort of, oh, you can't do that, you can't record it or whatever. And I was just telling Amit on the way here, actually, that I was at a quiz organised by the students. And this was last night. And one of the rounds was a voice round, and you had to do voice recognition. There was somebody talking in a very sort of sing-songy Irish accent, and we put it's Michael D. Higgins. That's what we thought. Oh, a silly little Irish accent, you know, but very wise and very talking about how the world is lovely, and we all have to go and get our crock of gold round the corner. And it turns out it was me. It was on one of my videos that I'd recorded for some final year course, and this guy, when he was a master's student, had nicked it. And anyway, yeah, sorry. The other thing I do whenever I give a talk is I prepare thoroughly. I have actually spent a lot of time, there were slight updates to another talk I've given, but over the years I spent a lot of time, or over the last couple of years, preparing these slides. And then when I stand up, I say the first thing that comes into my head. But I promise you, a bit like there was a lecturer I had, I was an undergrad at the University of Birmingham. It was a wonderful lecturer. He lectured on the history of maths and other topics as well. And he'd always start a lecture on one topic, then sort of open a parenthesis, and then open an anecdote on the parenthesis, and a parenthesis on the parenthesis, and then, but he always closed all the parentheses in the right order. And we finally got back to the topic of the lecture in the last 2 minutes, and he finished on time. Anyway, that's my ambition for today. So, Huygens clocks, or metronomes. Huygens was a Dutch physicist, a mathematician, and inventor. And he described an odd sympathy, and here's a sketch of what he did, when he had 2 pendulum clocks suspended on a shelf between 2 chairs. And he noticed that even though they had slightly different frequencies, they weren't perfectly the same, and they didn't start in synchrony, they started to oscillate completely in sync. And this theory has gone back to there, and it sometimes, if you do some Lagrangian mechanics, there's some theory of it. But here's some other examples. Now, these videos may or may not play, and I have no idea whether they're going to play online, and I have no idea whether you can hear the sound. I hope not, because not many of them have sound. These are fireflies. These are just most of these are videos nicked from the. Oh, it would be good if the sound played. And they. I see. If I do that, I'm getting myself broadcasted, which is great. So what I can do is maybe. Oh, it doesn't matter. I'll just hear myself broadcasted. That's fine.
No, probably you need to unmute yourself there. Maybe is it muted still there?
That will.
Yep.
Yes, that will work. No. Oh, but it's not mute on this. Oh, goodness, I don't know. I want to show you this one, then I'll turn the sound off. This is clapping. That now, there's nobody on the stage going like this. And there was a beautiful study that was done. I will turn the sound off now. These are electric generators, and it's used as a model of how the grid works. These are two generators with slightly different phases, and the guy's explaining to us how they have. You can see that they've got slightly different frequencies as well. And so when he puts a strobe on it, that white piece seems to be going round. And then he switches on a passive coupling between them, essentially just a resistor between them. There's nothing magic. And then suddenly they want to fall into sync. And this is not a video. And unfortunately, I've lost the video. But it was during a conference, the first, and I was about to say only, but almost only time I ever went to Beijing to a conference. And there at the gift shop at the Great Wall of China were a whole load of these waving kitties. And they were on some sort of table. And you can sort of see here that there's a wave such that all these kitties are almost in sync. And these ones are almost in sync too. And these ones are not quite in sync because they were at the end of the table. And so why do oscillators, no matter what they are, no matter what the physics, if they have similar frequencies and similar phases, why do they want to fall into synchrony? And that's the theory of, come on, I can do this. There we go. This is a theory due to Kuramoto. And it's a really simple theory. He says, throw away your second order oscillator equations and just imagine that you have an angle variable for the phase of something that oscillates. And it's just going to go at some frequency, omega. And then let's suppose that there's some coupling function. I don't know what it is, but it's small. So I've got here n oscillators, that's how the theory works. And it could be all-to-all coupling, it could be nearest neighbor, it could be random coupling or whatever. But these kappa ij's are fairly small things. And f, if you think about it, we want this f to have certain properties. I want this f to be periodic because these are phase oscillators. You want it to be odd. That means that you have symmetric coupling essentially, and you also you don't have to have this, but you basically a lot of things basically don't communicate if they're perfectly in synchrony. So this is something that will communicate. There will be some tension between them if they're out of synchrony. This is thought to be how neurons work. It's certainly how electronic circuits work. And then you just analyze these systems. They're really, really, really simple. You don't need the physics of what the F is. Yeah.
Alan, does it mean we are talking because it's periodic?
Yes.
So I'm assuming it's like suggesting indirectly that it's infinitely connected, infinitely long ranged. If you're
no, it doesn't have to be infinitely long.
Okay.
It's a finite theory. You can also talk about statistics of connections. You can talk about infinite grids, etc. But you can also do it with finite grids. So yes, you can use. I defer to the experts who can use the statistical physics and do all that kind of stuff. I just play with low order dynamical systems. And particularly in light of that question, I'm going to go from n is infinity to n is 2. And this is the simplest model. And the simplest model basically says, if I do a Fourier transform or a Fourier series of this f, it's basically got to be sine of harmonics of this phi I minus phi j. That's basically what the lowest order. So let's take sine. And so the simplest Kuramoto oscillator has this sine nonlinearity. If you take n is 2, you can do everything analytically. You can, you know, it's just a simple phase plane exercise. I'm not going to do it at 6:30 in the evening. But basically, you can show that there is a synchronous equilibrium, and you can look at the difference equation and just get a one-dimensional ordinary differential equation. I can look at the right-hand side graphically. I can just see, is the slope positive, is the slope negative, and you can immediately see that if the difference in the frequencies is small enough and the coupling is large enough, then the in-phase equilibrium is stable and the out-of-phase equilibrium is unstable, and the collective frequency is just the average of the two frequencies. You can extend that in a statistical sense to more oscillators, but it's essentially what happens. Now, I'm not one of your synchronization people. There are, you know, the University of Potsdam is basically full to the brim, I don't know why, of people doing synchronization. There are lots and lots of papers on Kuramoto oscillators and their applications, and it's really cool stuff. It's this button that I want to press. If you go to many, you can sort of, you know, average, and you can talk about coherence. You can have a measure of synchrony. It's a Kuramoto order parameter. I'm not going to explain it, but it basically says you can take something that gives you 1 if they're in complete synchrony. There's a sort of an exponential function you can apply to this that is 1 if they're in complete synchrony, and it's 0 if they're out of synchrony. And it's been observed with certain kinds, if you have lots of these, you get what are called chimera states, which are partially synchronous and partially not. They're sort of in the transition between synchrony and not. And sometimes people talk about crowd dynamics as being a bit like that. You have periods where people are really moving in synchrony, and other, sorry, not periods, spatial locations. Incidentally, there was a beautiful paper, and if you email me, I'll find you the reference, of people did some analysis of clapping. And what they discovered by analysing what happens in the Dear Leader's speech in various countries is that the normal rate of human clapping is just a bit too fast for, you know, the coupling is frequency dependent for synchrony to happen. But if you get a little bit bored and start to clap a little bit slower, then you're in the regime where it's likely to synchronize. So usually, you know, we talk about the slow hand clap. Usually in the Dear Leader's speech, when, you know, it's required that everyone in the audience has to give 15 minutes of clapping, it usually at some points descends to rhythmicity, and that's when the audience are just doing it out of duty rather than any sort of sense of enjoyment of the speech. So how are we doing for time? Right, good. Oh, what's happened there? Yes, don't touch it, Alan, don't touch it. And I won't go through that simulation. This is a simulation. I just nicked it from the internet, showing a whole load of oscillators that start slightly out of sync and showing how you get these chimera states, which are partially in sync and partially not. What I wanted to tell you about is the London Millennium Bridge. So there's this story, and the story goes, in the year 2000, they opened this amazing bridge between Tate Modern and St. Paul's. It was unusual in that it was almost horizontally suspended, such that when you looked at it from the side, it looks like a blade of light. Let me again turn the volume on, and I won't speak this time.
Aluminium and steel structure, a bit of great design and engineering that had thousands of people queuing to walk across it on opening day, 10th of June 2000. But as soon as the crowds hit the bridge, there was a problem. It wobbled, and not just a bit, but enough to make people cling to the handrails for security. Clearly, the crowds themselves were driving the bridge in a completely unexpected and very worrying way. The bridge was closed 3 days later and has remained closed ever since. But how could this have happened? Why wasn't it predicted? And
this is an experiment somebody else did to try and explain the theory, to illustrate the theory. These are Huygens clocks on tanks. They're not Huygens clocks, they're Huygens mechanisms. They've each got a slightly different frequency, and they're all set up at random phases. And there's a weak coupling, that's why Huygens clocks work, through the fact that they're on some very slightly flexible. It's really for me in some of the phases naturally. go on start to move. And the idea is that although people didn't mean to synchronise, they were all independent oscillators who just started to synchronise their footsteps. Then as the bridge started to move, they synchronised even more, and that caused the instability. And there have been nature papers and textbooks written about this as the sort of poster child of synchronization theory and why it can be dangerous and why it's unexpected. It's well known that bridges vibrate vertically when you walk in step, when soldiers walk across them. Most bridges have flexibility in this direction, but this particular bridge had flexibility in this direction, and that's how it started to wobble. But nobody was walking in step. So nobody was, there was no sergeant major going left, right, left, right, left, right, or anything like that. It was just this natural thing. And you can read a beautiful book on synchronization theory by Steve Strogatz. He writes beautifully. However, what actually happened? That video ended on the day it shut. Arup were called in. They were the engineers on the project. It was basically a collaboration between an architect and an artist to create this blade of light. But then they called in the engineers, and the engineers did some empirical measurements, and they calculated the force amplitude per pedestrian, and they discovered that as you got more pedestrians, so this force amplitude became positive. Now, what was this force amplitude? Well, it was a damping. So they basically said the bridge has some damping, but if you add people to it, that damping constant can go negative. What's a negative damping? It's like a positive feedback. And they basically said what pedestrians do, and they fit a line. They did experiments. They didn't take the central span. They thought that would be too dangerous. They took the end span of the bridge, and they did experiments of people walking across, and they found this empirical negative damping coefficient. And they did a whacking great retrofit. You see here, for example, to just fit dampers on the bridge, so that no matter how many pedestrians are walking across it, there's going to be more natural damping to overcome this negative damping from the pedestrians. And although I'd never read this in print, there was a sort of feeling, stupid engineers, this is a beautiful mathematical theory of synchronization. If they'd only understood that, they wouldn't have had to, completely damage this bridge by fitting these ugly dampers. However, engineers are not always silly. The pedestrians, this is a video of Matt Parker explaining in the Royal Academy, not the Royal Academy, the Christmas lectures, I don't know, about 5 years ago or something. And he said only 20%. And he analyzes that video. And he said, and other people have looked at that video and realized that only about 20% of people are synchronized. Now, if I'm looking at random signals and I say that 20% are approximately in sync, actually that means none are in sync. Because, by eye, you will always, if I look at 5 or 10 or 20 or 100 time traces, I'll say, oh, well, those are all of which have about the same frequency. I'm going to by eye say, well, look, a fifth of them are roughly similar. There is no evidence of synchronization. And in fact, we did and other people have looked at evidence of synchronization causing instability. And in fact, it had been known before. And there have been examples, sort of, very sadly, after this event, in Cambodia, where the bridge wobbling caused a stampede. It wasn't the bridge collapse that killed the people, but the stampede resulted in, I believe, is about 100 deaths. And there was also one on the Auckland Harbour Bridge, when there was a Maori protest going on, marching over the bridge, and it was seen to wobble. There's also something that's not quite right. If the pedestrians aren't synchronizing their frequency, why would they choose the natural frequency of the bridge? Something else also has to happen. If the pedestrians are going to be like these clocks, why do they have to choose? The bridge isn't like a passive device. It's something that has a mode of vibration, and it's different to the walking frequency. Why would everyone start walking at that frequency and excite it? And how would this synchronization theory explain what is the critical number of pedestrians required to trigger the instability? Because it was observed in the Arup data that you have to get sufficiently far. And why does the negative damping explanation work? And do pedestrian walking frequencies really need to be tuned to the bridge? And the answer to all of those is no. There's a much simpler theory. In fact, there was a letter in The Guardian 3 days after it opened from the Nobel scientist, Brian Josephson. This is just showing that there have been 25 other examples, etc. And my colleague, John MacDonald, is a bridge engineer, and he had done his PhD on the second Severn crossing, and something happened in Bristol. In fact, something happens every year in Bristol. There's a balloon festival. It's Europe's largest balloon festival, and it's just across the Severn Bridge, just across the Clifton Gorge from the city centre in the park over there, and everyone walks across to go to this festival. And on 2 of the evenings, there's a night glow when all the balloons are lit up and fill the night sky with balloons that are alight. It finishes at a certain time, and everyone crosses the bridge at a certain time to go back. And it was observed that the bridge had started wobbling. This was after the Millennium Bridge thing. So none of these things were dangerous, by the way. That Cambodian example was dangerous for a different reason. I don't believe any bridge has ever collapsed because of this. It's just inconvenient and people don't like it. So the next year, there was a predicted day when this would happen. That's very unusual for instabilities. They knew when it was going to happen, so he instrumented the bridge. And he measured exactly what was happening. And what he found was the following. What he found was that there were 2 different frequencies that were excited. And this is also showing, this is across the whole week. There were 2 days when the lateral frequency of this bridge started to wobble. Good to see you. I'll cut to the chase. This theory works. The other theory doesn't. And this theory comes from trying not to fall over. So nice to see you. Yeah, have fun. But moreover, he discovered during these night glow events, where there were these 2 large peaks in the lateral oscillations, there were 2 different modes of the bridge that were excited. There are 2 different frequencies. One is sort of the bridge doing that, and the other is the bridge doing this. How could pedestrians simultaneously synchronise to 2 different frequencies? It essentially blew that theory out the water. Nobody noticed. The engineers knew, but the popular media was still, this was the poster child of synchronisation theory, etc. So, what happened next? Well, if you're walking on moving ground, what do? You try not to fall over. So if you start to feel yourself going that way, you brace yourself against the direction you feel yourself moving. Well, what does that do? That stops your energy moving in that direction, but that energy has to go somewhere. That momentum has to go somewhere. Where does it go? Into the motion of the bridge. So in trying to brace yourself against falling over, on average, it's slightly complicated because you only get a chance to do that bracing once per footstep. And so it is a question of timing. But in general, you're going to add lateral energy to the bridge. Any small movement in the horizontal direction, no matter which speed you're walking at, no matter if you're walking forwards or backwards. If you look back at that video, the London Millennium Bridge, people are walking in both directions. You can't simultaneously synchronise your footsteps if you're walking in 2 different directions. It's a frequency-independent instability. And in fact, it's a very well-known instability. It's just, in fluid mechanics, this would just be called flutter. It's just a positive feedback mechanism. But the fact, this is a sort of, if you like, a granular media kind of analog of fluid flutter. So what can you say? What you can say is that we could do some analysis. How did we do some analysis? What you can do, and what other people have done, is create massive biomechanical models of people, finite element models of bridges, and you can get any numbers you like. So what we did is try to come up with the simplest possible theory, and then we had to go into sort of biomechanics. And essentially, there's the frontal plane dynamics, the side to side, and there's the fore aft, it's called the sagittal plane dynamics. So essentially all we say is the sagittal plane dynamics looks after itself. You just put your feet down as like a clock. And different theories say that those can be adjusted or not adjusted. What matters is how much lateral, if you like, how wide are my feet? And then some of the videos, I won't show them, you get sort of people doing this sort of drunken sailor type walking as they brace themselves, as the as and you see this on boats, for example, when people try and steady themselves on boats. So we came up with some very simple models, and we both simulated and analysed them. And to cut a story short, the theory works. These are really simple models. They're just, you know, you can fit the data to the modal mass of the bridge, etc. You can fit data to the, so you have a bridge and lots of pedestrians. And then what this function needs to be, the forcing function of the pedestrians, this is going to be some piecewise smooth function that depends on how you put your feet down, but they're ridiculously simple. And we had, in fact, three different functions that we tried, and they all do the same thing. Of different, and I'm not going to go through the asymptotics, but basically you can smooth, because everything's over a one period. You can just do averaging. You can just use the theory of averaging. You can pick up, you can imagine that you were Ali Naife or something, and look at the theory of averaging 101, and just do it with your bare hands. It is not difficult. It's the sort of thing you know, if you have a course on perturbation theory for third-year undergrads, it's the sort of thing we teach. That's all you do. And basically you get this amplitude equation, or sort of master, in stochastics you call it a master equation, but here we call it a slowly varying amplitude equation for the bridge, and it has a damping coefficient. There's too much on here, I'm very sorry, but you do the method multiple scales, and you want to know what happens to the phase dynamics on a slow time scale, what happens to the amplitude dynamics, and what you find is that basically there's the amplitude x satisfies some equation that looks like this, and that leads to a solvability condition. It's just what you would normally do, and you end up, the slow dynamics looks something like this. So what does this mean? This means I've got some, the phi dynamics does something like that, but the sine component gives you the thing that you want, and it's this thing here and that thing there that represent your damping coefficient. If you get first order dynamics rather than second order, but they basically represent your damping coefficients. You can calculate it. All these things here are just averages over pedestrians of things I can calculate. And so we came up with a theory that shows that as you increase the number of pedestrians, we get negative damping. That's because nu, I haven't told you this, is a rescaled n number of pedestrians. So provided this number here is positive, then we will get negative damping for a large enough number of pedestrians. And it turns out this number here is dominated by this here. I'll tell you what those three effects are. There's basically three things that contribute to the negative damping. One is the dependence of the average lateral force on the bridge velocity. Then there's adjustments to how you place your feet in the lateral plane, and adjustments to how you place your feet in the sagittal plane. And different models have different numbers of these, but they all do the same thing. For a very wide range of frequencies, they give you this negative damping. As I say, it's all a question of timing. So we did a numerical thought experiment. In the numerical thought experiment, we tried and kind of failed to, we talked about putting these pedestrians on a bridge, and this was a PhD student. I should have said this is a collaboration with a number of people. I'll tell you who in the end, but it involved a group in Atlanta, Georgia, in Georgia State University, not Georgia Tech. And one of them was really good at computer graphics as a PhD student there. And so he created, there are videos as well, which I won't show you. And we referred to the pedestrians as sort of Nigel and, you know, whatever. And you may recognize that font. That is the font of the N from Nature, but they still wouldn't publish. Well, I think it came out in Nature Communications or something. You've got to try, haven't you? Yeah. And the thought experiment is we'll just add pedestrians one at a time on an infinite bridge, on an infinite bridge, let's say, effectively, although the stiffness in the bridge is finite. Or you think of it as adding pedestrian density one at a time to the bridge until you reach a threshold where it goes unstable. And what you find basically is the bridge amplitude after a critical number of pedestrians in all of the models, it goes unstable. This was the simplest model. You get something unphysical. This model doesn't have any adaptation to the timing of when you're putting your feet down. So it allows you to sort of put your foot down, but ridiculously wide over there and still do it at the same rate. These two models are more like it. And what we actually find is that synchronisation high is the synchronisation is the thing that causes the saturation in amplitude here. This thing doesn't go off to infinity. So these were just numerical results, and they match the theory that I showed you. So I'm almost there. This shows you how this is the ratio of frequencies for two different models here. I can't remember what the difference between the left and the right is. I do apologize.
Sorry, Alan, what's the bigger capital omega and what's the small omega?
Yes, capital omega is the bridge frequency. Little omega is the average frequency of the pedestrians. We've got a distribution of frequencies, but that's their average frequency.
Given the fact that you have people coming from both sides.
It doesn't matter. Well, because it's the lateral part of what they do that matters. So a positive frequency and a negative frequency, I call a positive frequency. All that actually matters is the frequency with which they're going.
The beat frequency.
Yes, we don't have any. I mean, we do now have models. That's the latest thing. We've got a grant proposal in there where we want to look at the social force dynamics of people clogging up and seeing whether that exacerbates or eases the situation. That's and we're trying to do things which are a bit more practical. But in this theory, there is no clogging up. Pedestrians just walk at a frequency they want to. They will adjust their frequency as the bridge starts to move, but they won't adjust their frequency if the bridge gets crowded. And so we don't actually care where they are in the bridge, on the bridge. We've essentially assumed, I mean, you can be more sophisticated this. We've essentially assumed the mode of vibration of the bridge is like that, which of course isn't true. It's going to be like this or like that or something. But this is a simplified theory. So the direct conclusion is that synchronisation, if it is observed in 20% of pedestrians, is a property of the instability. It's something that happens at finite amplitude. Of course, as the bridge starts to move, people are going to start to walk in synchrony with it. But it isn't the cause of the instability, at least we claim not. Causality is a very difficult thing. It doesn't explain the instability. Pedestrians are not like Huygens clocks, and the bridge is not passive coupling at all. This is a very different kind of instability. It's not that the instability is at the common frequency of the pedestrians. The instability is at the frequency of the bridge. It's you're providing a negative damping. You're providing a push me, pull you mechanism to the mode of vibration that the bridge wants to go at anyway. It's like an active damper that's or a control device where the gain has been turned up too high. Synchronisation theory requires tuning of pedestrian frequencies, and it gives no insight into how to say what is a safe or not safe bridge, other than to give it as much damping as you possibly can. Whereas our negative damping theory is intuitive. You give energy to the bridge to stop yourself falling sideways. The effect can be measured, modelled and simulated, and it's robust to, even the simplest mathematical models, and we took 3 different ones, can do the same thing, and it explains instability across a wide range of different bridge frequencies. It doesn't require pedestrians to all walk at the same speed, and it gives, this is overstating it, because actually this N crit is dependent on all kinds of things. What we want to do in a new grant is to look at heterogeneous populations of pedestrians and actually try and understand what's going on. And the engineers were right all along. This idea, stupid engineers talking about negative damping, clever mathematicians talking about this beautiful synchronisation theory. No, mathematicians were trying to find an application of their theory without thinking. And the thinking that they failed to do is the idea of when something goes unstable, you immediately think resonance. You think resonance. But actually, instability is very rarely due to resonance. It's actually due to a Hopf bifurcation if something oscillates, which is a negative feedback type. There's no resonance in flutter of an aircraft wing. And actually, they were just trying to make a more complex theory than necessary. And also, people were put off because when you look at those videos, and I won't show it again, you do see people swaying from side to side, but that's their heads. That's not the force they're putting with their feet. It's also, you're looking at the finite amplitude effect and the wisdom of the crowd looking at the thing, wanting to see what they want to see. This was much earlier work I did, and I realized it was exactly the same theory. This is work I did maybe 10 or 15 years ago about how insects hear. And within the insect kingdom, there are all kinds of different hearing mechanisms, of which the mosquito and related things have the most sophisticated. And what mosquitoes have is remarkable direction sensitivity. So they have an organ, this is a slice through it, which has 60-fold symmetry. So this is one slice through the 60-fold symmetry. And that organ is like an upturned umbrella. And they are remarkably good at listening to one frequency. So whereas we have multiple tuning forks in our ear, they have as many neurons inside their hearing organ as we do in our inner ear, but it's basically tuned to hearing at really low volumes. The frequency, or the males have twice the number of neurons as the females do, him listening to her frequency. And that's how they do sexual selection. They even do that in the free. There's another project we have with the same insect biologist. They do courtship in the frequency domain. There's a sort of, any note you can sing, I can sing higher, and they lock into each other's wing beats frequencies. Also, males swarm by avoiding each other's frequencies locally, and then globally having a very loud frequency. And then when a female comes along, the swarm breaks up and they each try and do the frequency matching thing. But the hearing organ is really interesting because it has, a bit like our hearing system does, it has an active hearing system. And how the active hearing system works is each of those neurons is surrounded by an organ that's called a scolopedia. And a scholopedium, it's not spelled like, there's a website called Scolopedia. It's spelled completely differently, but it's basically got dynein molecules, a bit like in sperm flagella, etc., that can cause an active twitch. So when it opens an ion channel, as the neuron detects that there's been some movement and so that something is hearing, and then it's a sort of push me, pull you mechanism. So you open the ion channel a bit, it pulls. It actually has something that will pull the flagellum further. So this thing is not only listening, it's actually pushing the air. Our ears do the same. They're called otoacoustic emissions when you're alive. And it's one way that we test babies' hearings. You put a click and you listen to what comes out. And insect hearing's the same. They're essentially tuned at very low sound levels. The problem with that is, if you, it's the same with our ears, if you have a very high sound level, you're going to kill it. And so they have this device, this push me, pull you mechanism, also has a sort of timing device that it then twitches twice to turn off. And the second twitch is whilst, the first twitch would sort of pull you in the right direction. The second twitch will pull you, but too late, after the oscillator has started to go the other way around. So it acts as a brake, a suppression mechanism, as well as an excitation mechanism. Similar theory, synchronization is hugely important in power grids. Basically, if you know anything about AC circuit theory, everything has to be in synchrony for the grid system to work. So the phase coming out of that plug there has to be identical to the whole of the grid across the UK. And if I turn my kettle on, some power station somewhere has to work that ever so slightly harder to keep it in synchrony. One of the good things is, because there's high inertia on the system, it turns out that the Kuramoto mechanism keeps everything synchronous. But if you lose high inertia, that synchronization mechanism no longer works. And in the era where we're moving to renewable energy rather than big rotating machines, keeping the network synchronous as well as matching load of power is a big headache for the grid operators. And then in neuroscience, I've been working with some neuroscientists, the pituitary gland to release dopamine, they need this stimulus from the dorsal vagal complex in the brain. No, it's not. It's from the these TIDA neurons in the pituitary gland. Everyone knows them as TIDA because no one can pronounce whatever that is. And they need to synchronize in order to secrete the hormone. Otherwise, they're a noise signal. And they seem to be things that want to burst, but the way that they're coupled through gap junction and also, which is a sort of direct electrical coupling, synaptic coupling, not synaptic, sorry, cell body coupling. There's a sort of, fairly large coupling as well as through the synapses, seems to, and here's some data that Jake recorded, and he defended his PhD on Monday. Closing remarks. I showed you an alternative, simpler mechanism for synchronization. I'm not saying, there are many things for which the Kuramoto theory is bang on, but it's negative damping on average, but there's a hidden global frequency. In the case of the mosquito, it's the frequency that the stiffness of the arm is actually set to listen to a particular frequency, namely the female's frequency. At the bridge, it's a mode of vibration, and everyone is trying to accumulate on that frequency, and it's a Hopf bifurcation, not a resonance. Kuramoto synchronization of near identical oscillators is a beautiful theory. It's a really simple theory. You can teach it to the undergrads and they really get it. And you can show examples of things that synchronize. There are also myths about synchronization that are not true. For example, it's not true that women's menstrual cycles tend to, if they live in communes or whatever, that's an urban myth. It may be true, but it's an urban myth that's an example of synchronization. And I would say that the London Millennium Bridge is an urban myth that it's an example of synchronization. It's an oversold theory. But the Kuramoto synchronization theory is a beautiful theory, explains many things, but not bridge instability. And possibly, like Thomas Huxley said, maybe this is the great tragedy of science, the slaying of a beautiful hypothesis by an ugly fact. Actually, I would say not. I would say it's the core principle of mathematical modeling, which is keep it simple, stupid. It's called Occam's razor. What is the simplest theory? And it's a question of thinking what is the simplest theory. If there are two explanations of an occurrence, the one that requires the smallest number of assumptions is usually correct, or try not to fall over. I just want to thank a few people. These are my collaborators, my colleague John McDonald, Igor Belik, Kevin Daly, who were at Georgia State University, Matt Bossian, who had previously worked with John McDonald, and Alan McRoby, we're proud to say, was on the synchronization paper, and we recruited him as a co-author onto ours. So he supports both theories. These are the people I've done some of the neuroscience with. And finally, a dedication. My colleague who got me into this died suddenly almost 2 years ago now, and I'd like to dedicate this to him. Thank you.
Yes, yeah, we need to be clapping, yeah.
Yes, exactly, yes. Keep going, yeah.
Alan,
yes.
I can start with a question from my end, of course.
Yeah.
And towards the end of the talk, what you mentioned about the dynamics.
Yes.
Because it's an actioning mechanism.
Yes, it is.
And one of the standard problems related to molecular motors, the long-standing one is the nature of the walk. And one is, so just to clarify, if this is a one-dimensional track, one can walk like this, or one can walk like that.
Yes.
Which one is the more preferred mode?
I honestly don't know. There's something even more basic we don't know. We don't know because, mosquitoes are, they are a model organism, but they're not, fruit flies are studied way, way more than mosquitoes. We don't know whether the dynine, the structure of it makes it look like, it's rather like the flagellum in that they have these pairs, they have sort of 8 pairs or whatever. Yeah, whether or not it contracts like that or it contracts like this. My suspicion, just looking at the geometry, is that it's well designed to contract like this, but I honestly don't know. I do know people who model these molecular motors, but I don't think that's ever been done in the mosquito, as far as I know.
Yeah, no, the reason it came to mind is basically mapping it to the model that you saw.
Yes.
So basically, one is a frequency going like this,
yes,
or like that. So this could as well. I mean, an extended version of that. I don't think anybody has tried.
Oh, I see. Yes, I don't know. Again, it could be. What is the question? What is the question? You're trying to understand molecular motors and the whole myosin dynin myosin motors, etc., and the fundamental mechanics of what happens. I don't know. As soon as you get down to that level, there are some huge mysteries. When you try and get down to thinking of biochemistry using classical mechanics. So biochemistry is full of long thin molecules. There's one basic mystery which I don't understand, which is when proteins are formed, they're extruded in a long line like this, in a long chain. And conformation is basically a process. So think of it as like this wire here. This wire here is extruded. Oh, I probably shouldn't have unplugged that. Whoops. Yeah, it doesn't matter. Some wire somewhere is extruded, and it's basically like this. And then thermal processes, that was a huge mistake. Sorry for those people who are online. A huge mistake, because it's like somebody's got the thermal processes then is like a big ball of string that gets, and every single time it has the same conformation. Every single time the protein is formed in the same conformation, and nobody really understands. You know, there's something we don't understand about the thermal processes going on, but it's like buckling, and it always forms the same shape amongst many, many equilibria. It's not even clear to me, although the central dogma is it forms a minimum energy configuration. I'm not sure that that's right.
About that part, I mean, talking about the 9 to 1,
yes.
And these are tubules. So basically,
yes.
Tubules like two wires sliding on each other. That's something that we worked on a while ago.
Oh, cool.
This was the work with Frank Edition.
Okay, yeah. Send me an email with a reference. Yeah, I mean, I've not thought about that, but the insect biologist has gone on to do some other things now. But yeah.
The walking problem is
yes. No, I bet it isn't. I remember Peter Ashwin talking about that a few years ago. Famous protein folding problem. Whoever solves it, yes, somebody's put online, will earn a fortune. Yeah.
Yeah, it was still there, although it doesn't show there.
Yes, quite.
It still is. People can see it.
Yeah, question.
So, talking about the encrypt for the
yes.
problem.
Yes.
Were you able to correlate your encrypt with the Millennium Bridge
data? Yes. Or? Yes. With a little bit of fudging, I've got to be honest. Yeah, but you can. You can.
Even with a little bit.
Even with a little bit of fudging, yes, you can. Yes, you can. Yeah.
And if you were to account for, because the model didn't at all account for the fact that people tend to synchronise as they're walking along their own step length, right?
So it's interesting, isn't it? It depends what people are doing. There are whole theories of social dynamics, and that's what we want to get into a little bit. There are theories of pedestrian motion that are a bit like theories of car drivers. Basically, there's a speed I want to walk at. You know, obviously, if everyone's together in a friendship group, it's different. But if I'm, just a random bunch of people, I want to walk at a certain speed. But if there's somebody in my way, I will slow down to their speed for a while. I will also try and dodge them. I will, so there's a sort of, in vehicle dynamics, it's called a speed headway function. Dirk Helbing is one of the main proponents of this, and my colleague Eddie Wilson as well. Doesn't quite answer your question, but if you want to get more realistic, it gets very hard very quickly. And then you say, well, what is the question? And, we haven't really got any further than for the practical bridge designers to say, add as much damping as you can.
There's a comment.
Yes. Yeah.
The famous protein folding problem, whoever solves it will get an award.
Yes, indeed, yes. Yeah, I think that's right, yeah. Some big mysteries there. Anyway, it's all fun. I mean, that's, I love just playing with little models. And I just assumed that this theory was right, but I've never thought about it. And it's fundamentally, it's not likely to be right. It requires, it's somebody looking at something and saying, oh, I bet that's synchronization. And then the bandwagon, that's why I called it the wisdom of the crowd. People jump on bandwagons. And whilst Kuramoto theory, has hundreds and hundreds and thousands of citations, it's been over-applied, at least in this context. There are other examples like that. I mean, no, I won't. I'm not going to diss areas of mathematics, but I also work a bit in nonlinear waves. And the number of papers on the Korteweg de Vries equation or the nonlinear Schrödinger using integrable systems theory, if I picked a bag of if I had a bag of nonlinear wave equations and I picked one out at random, it wouldn't be integrable. But it's a beautiful theory. Very good. Thank you very much for having me. Yep.